Good morning, team. Chemistry coach coming at you with a pre-lab video. So we did the kinetics pre-lab video earlier. I think that's lab 8 for our class. And the activation energy will be lab 9. These are our two labs that deal with kinetics from our chapter 14 that we've been tested on. You did the work, so your knowledge of the mathematics should be pretty good. They are very similar labs. So if you review the kinetics, and I highly recommend you review the kinetics pre-lab, it talks about the 3 different reactions going on in order to keep one of our species constant. We're going to do the exact same reactions for the activation energy lab, but we're going to vary it a little bit. Now, this was the equation of interest. This was equation number 1 in the kinetics pre-lab video. Some peroxydisulfate ion reacting with some iodide ion, producing the triiodide ion, and a couple of sulfate ions. And what we did in the kinetics one is we had a second reaction where the triiodide came down and reacted with thiosulfate, which regenerated your I- and kept the I- constant. So same thing with the other pre-lab. I'm not going to talk about that again. When that thiosulfate ran out, equation 3 came in and the triiodide reacted with some starch, which turned it blue. Exact same thing. And we can measure the change in time and the change in concentrations and whatnot. We're going to do a slight twist on that. In the kinetics lab, what we did is we altered the concentration of the peroxydisulfate and then measured how long those reactions took for a set amount of constant iodide. And we were able to get the rate law from that. And if I recall, our rate law was K times the reactants, the peroxydisulfate ion, times the iodide ion. And those were both values of 1. So A was 1 and B was 1 for that scenario. Oh, I just gave you the answer for that at kinetics lab. Anyway, not too tough. They're usually going to be 0, 1, or 2 anyway. So if this is our rate law, let me put a box around that. That's our rate law. How we're going to change it for this one, instead of altering the concentration of the peroxydisulfate, we're going to keep that constant. So we're going to keep all the concentrations the same. We're going to do this at four different temperatures. So we're going to be in lab, and I'm going to make, and I'll video this. I'm going to make 4 different insulated containers with a set amount of ice. And I'm going to set those at 4 different temperatures and use the thermometer to measure those temperatures. And we're going to run the same concentrations at those 4 different temperatures and measure the delta T, how long those take to react. Right? So look at some of the theories of kinetics, and you can kind of anticipate if it's a warmer temperature, will it react faster or slower? When we do this, and we're going to do, and this is in your lecture notes, so I'm going to review it a little bit, but make sure you check out some of your lecture notes under the activation energy and all the fun stuff we did with that, some of the plots. And you should have done this in some of the homeworks as well. We were able to do a graph, and from the slope of that graph, we could figure out the activation energy. We're going to do the exact same thing. So since it's not a skills-based lab, it's a very simple one. You just slosh a couple of solutions together. Measure the temperature. I know you can do that. Measure the time. Read a clock. I know you can do that. So I'll do it for you and video it in lab. And when I'm able to get in there and do that, then I'll post it. I'll announce it when I actually get that. And that'll have all the data. So I've already put the data sheets and calculation sheets under the Canvas. If you look under the files folder for my class in Canvas, click on lab. And in there, you'll see folders for activation energy lab, kinetics lab. You'll find your data sheets and calculation sheets. So make sure you print those out, or you can write on them directly. But when I get the video I make from lab, when I do it, you'll be able to get all of your primary data from that and write it in your data sheet. And then you can do your calculations in pencil. And when you've got those, I'll put a set time limit on it. And then you can email me all of the data sheets and calculation sheets, and I'll grade you based on that. So I'm not worried about these ones. These are not technical labs. So we're good doing these virtually. Let me pause it here. Well, let's talk about rate real quick. Remember how to calculate rate? We can set up the general rate of the reaction with any species. We're going to be doing it with respect to this. So that'll be the loss, or so the negative of the change in the peroxydisulfate ion concentration over the change in time. So remember, we did that for the kinetics lab, how to calculate the rates. I'm going to take the Arrhenius equation, look that up in your lecture notes real quick while I pause this and put up a new board. And we're going to manipulate that Arrhenius equation, create an equation in a y equals mx plus b format. And so we can make a graph and determine the activation energy from that. It's really cool. We've already done this. I know I did it in lecture, so look back in your lecture notes and you will find that exact same process. So try to review that before I actually do this. See you in a second. All right, guys, remember the Arrhenius equation. That allows us to measure the rate constant. So it took all that fun stuff from collision theory we talked about, where reactions, they have to collide with the right molecular orientation. They have to collide with a collision energy greater than or equal to the activation energy. And it's all summarized quantitatively in the Arrhenius equation. I told you this name would keep popping up. So remember, the rate constant was the pre-exponential factor. And again, that pre-exponential factor, capital A, actually represents two other factors. It represents the collision frequency, that was the Z naught, and the probability of that collision having the correct molecular orientation, which was a P. So that's actually P times Z naught. Just collapse those two variables into A, the pre-exponential factor. And we multiplied that by E to the negative EA over RT. And again, that's the activation energy, E sub A. R is the universal gas constant, and we're going to be using the one with energies, the 8.3145 joules per mole Kelvin. We'll write that down later. And then the temperature, of course, will be the Kelvin temperature. Let's manipulate this real quick. Remember this fun stuff? I know you missed all this algebraic, physical education stuff. Here we go. Let's take the logarithm of both sides, the natural log. So we're going to get the natural log of the rate constant is the natural log of AE to the negative EA over RT. And remember, stupid log tricks, if you take a log of AB, that's the log of A plus the log of B. So we can split the pre-exponential factor from the E to the negative EA over RT. And again, the E to the negative EA over RT term kind of represents the fraction of molecules that upon collision have a collision energy greater than or equal to the activation energy. It's more of a statistical distribution there. So let's split these two. So now I can take log of the rate constant is log of the pre-exponential factor plus the log of E to the negative EA over RT. And obviously if I take the natural log times the base E here, E to the X, those cancel out just to give me 1. And then I'm going to flip these. So I'm going to get the log of the rate constant will be negative EA over R. I'm going to put 1 over T in parentheses plus log of A. So if you look in your lecture notes from the kinetics chapter, this should look familiar. This is your y equals mx plus b format. So the log of the rate constant will be your y-axis. The 1 over temperature value will be your x-axis. Your slope is m. That will be negative EA over R. We're going to be using that right on. And then the log of the pre-exponential factor is your plus b, or your y-intercept. Good little review there from our kinetics activation energy talk. Now if we make a graph, right? The chemists are always trying to get things in a y equals mx plus b. Let's make a plot. And you're going to make this plot for this lab once we get the data. If we plot the log of the rate constant, and you'll be able to calculate the rate constant, and this is what one of your Prelab, I'm not going to do this for you, this is in your Prelab in your general chemistry notebook. If you know the rate law, and you know the concentrations of the species, and you know the rate, I showed you how to do the rate on the last board, you should be able to calculate the rate constant for the 4 different temperatures we're going to be running this at. Just take the natural log, and you got your y-axis data. If we plot that versus the x-axis, which is the inverse of the temperature, which would be Kelvin to the negative 1 power. Well, I'm going to give you the temperatures in degrees Celsius. Of course, you'll have to convert that to Kelvin and then take the inverse of that, plot that. We should get a negative slope, right? Because the slope is negative EA over R. So we're going to get a negative slope like that. The y-intercept here, which if you do a least squares fit on your Excel, on your laptop, which you should be able to do, right? I mean, you need to turn this in with your lab. I want that graph. That's a key graph because we need the slope from that. You do right click on any data point, add trend line, add equation to chart. It'll give you the y equals mx plus b. You could actually calculate the pre-exponential factor if you wanted to. I can't remember if it asked for it in the lab, but hey, if you're bored, you got tons of time, you could do that. But we're looking for the slope. And we know that's negative EA over R. So once you get the slope from your least squares fit, just move the negative sign over and multiply it by R, 8.3145 joules per mole Kelvin. You probably have to convert that to kilojoules, I think. And you'll get your activation energy in kilojoules per mole. That's the goal of this lab. So let me pause it. I'll talk briefly about what I will be doing in lab and how we do some of the calculations, and we'll be ready to roll, right? Watch this video, download the data sheet, calculation sheet, and once I get the video up of the data, you'll be ready to rock. All right, guys, you like my colorful board here? So hopefully on the video, you'll be able to envision this before I do it. But what we're going to do is we're going to take 4 styrofoam containers, right? I'm going to stuff 3 of them with ice and 1 of them without ice. That's what we're going to do. And then I'm going to put beakers inside those. I'm going to put more ice in here and less ice in these and then no ice. So this will be at room temperature and these will be colder. So I'm going to get 4 different temperatures from coldest to warmest. And I'll just stick a thermometer in there. And what we're going to do is we're going to take our 2 solutions. Remember, in our reaction, we've got the peroxide disulfate concentration, solution, and the iodide solution. So each of these, so all the red test tubes will be sitting in this beaker with some water set at a particular temperature, right? 4 different temperatures, coldest to warmest. I will have the exact, as close to exact as we can, but we're going to pipette in, ideally, I think it's 10.00 mils, but the volume doesn't matter. We're going to have equal volumes, right? I'm going to have a certain volume of the peroxide disulfate in the red test tube and the same volume of iodide in the green test tube. Now, in the iodide, I'm also going to have the thiosulfate, the S2O32-, and the starch, just like the kinetics lab. We're just using test tubes in this lab rather than Erlenmeyer flasks like we did in the kinetics lab. So I'm going to have those separate. They're not going to be mixed yet. And I'm going to put them in there at that temperature and let them sit for about 5 minutes so they come to thermal equilibrium. So the solutions inside the test tubes will be at that temperature. And once they're at that temperature, I'm going to mix those test tubes. I'm going to mix those together. So I'm going to take this test tube, pour it into there, pour that one into there, pour that one into there, pour that one into there, mix it up real good, shove them back in there. So we're going to run these reactions. So one of them will be empty. The red ones will be empty. The green ones will have both solutions in there. The reaction commences. That will be T equals 0, T initial. And I'll show you a picture of the clock at that time. Then we sit there and pick our nose until they turn blue. Boop! That's the final time. I'll take a picture of the clock at that time, and you can calculate the change in the time based on that, right? And at the 4 different temperatures. And you'll be able to calculate the initial and final concentrations exactly like you did in the kinetics lab. So look back at that pre-lab where I'm going to show you how I make this solution, right? That'll be your first M1V1 equals M2V2. Again, we're going to be doing a double dilution. The original solutions in each test tube, you'll have to calculate before mixing using the dilution equation. And then when I pour these 2 test tubes together, that process of mixing the 2 solutions dilutes it again. So you have to do the M1V1 equals M2V2 a second time for each one of these. At least it's only 4 instead of 6 like it was in the kinetics lab. And then you can calculate your concentration changes. You'll be able to calculate your rates. You'll be able to calculate your rate constants and then make that graph. So I'll give you all that primary data. Very straightforward lab. And then once you calculate that activation energy, send all your data to me and I'll grade your lab. It's actually kind of a fun lab. I can't wait to go in and do it. Enjoy, guys.